For our second lesson in our 10th unit dealing with surface area and volume, we're going to focus our energy on pyramids and cones. We've already determined the surface areas for both prisms and cylinders. Really noting the difference between those formulas is just using a P for perimeter in the base of a prism and C for circumference in the base of a cylinder. We're going to have a very similar relationship for the formulas in pyramids and cones in the surface area as well. So our goals today are to calculate the surface area for pyramids and our surface area for cones. We also have a little bit of vocabulary to get out of the way. I know that it's no fun to write this down, but we just want to make sure that we understand what a pyramid is, and specifically understand that we're going to be working in the context of using and finding the area, surface area, and the volume for regular pyramids. And now when we talk about a regular pyramid, this is typically what we imagine if we are to picture a pyramid in our brain. We typically think of, the Great Pyramids in Egypt, and those are defined as square pyramids, where the base is a square, a regular quadrilateral, a regular polygon, and then the lateral faces are not only isosceles triangles but congruent isosceles triangles. So we're going to focus our energy on regular pyramids. However, it's helpful to note that we have a little bit of anatomy to discuss there. The base, obviously, in the pyramid is typically a square is what we're going to deal with. In some cases, we'll have an equilateral triangle. We may have a regular hexagon for a base, etc. But we're going to try to focus on regular or pyramids with regular polygons as their bases. And all of these lateral faces are these triangles, and all these triangles meet at the single vertex. At the top, obviously there's vertices on the corners of the square bases, but each of these triangles are congruent. And so when we're finding the surface area of this pyramid, we're simply going to find the areas of these four congruent triangles, add them together, and then find the area of this base. And so we'll try to streamline that with our work. But it's helpful to note that we have the lateral faces are these triangles, the areas of these triangles, and then we have also the area of the base that we need to add into our work. Now the altitude of our of our pyramid is the perpendicular distance from this vertex at the top to the center of the base, to the center of the pyramid's base. That height, or that altitude, is that segment. The distance there is called the height. But then there's this other notion of the slant height, and that is how tall one of these triangles is. Now, these triangles, this is a little hard to visualize because we're trying to have a two-dimensional understanding of a three-dimensional concept, but you should notice that the height of one of these triangles, if I were to sit it perpendicular, is actually taller than the height of the pyramid itself. And that's because the height of this triangle is like the hypotenuse in a right triangle that cuts through the profile view of this pyramid. So what I mean by that is, if we were to draw from a vertical segment from the tip top of the pyramid, we would have this be the height of the pyramid, this be the slant height, which we're going to use L for that, and then for this distance to be half of the side of the base. All right, and so that's kind of this profile view right here, where we are cutting straight from this vertex to the center of the base. That's this h value. The lateral height, or the slant height, there is the hypotenuse there, the height of this triangle, and then this portion right here in this right triangle is half of this base. We can probably explore this a little more in class. It's a little hard to visualize here in this kind of video rendering here. I'm sure that someone can make a fancier animation if you want to look that up on the old YouTubes. But in this right triangle, we should know at least two of these pieces of information so that we can find the third using the Pythagorean theorem. Sometimes using a Pythagorean triple is obviously the shortcut way to go. Typically, we won't know the measures of these angles, so we won't be using trigonometry or special right triangles for that matter, unless we have a relationship that we've already kind of understood based on the two side lengths. All right, so from there, let's go ahead and talk about that lateral area. Again, the area of these four triangles, or in a triangular pyramid, these three triangles, all right, that make up the lateral faces. and then of course finding the area of the base as well. So we're going to do that work. The shortcut for the lateral area in a regular pyramid is to recognize that these four triangles are congruent to each other. And so if we can shortcut that to make our lives a little bit easier, then we want to do that. All right, so what I mean by that is we know that the area of one of these triangles, if I can use my arm strength, there we go. The area of one triangle is 1/2 base times height. Well, the base of one of these triangles is simply a side of the square or a side of our equilateral triangle. And then the height of this of one of these triangles is that L value, that slant height. So the area of one of these triangles is 1/2 times one of the sides of our base times the slant height. So for all triangles, all four triangles here, or all three triangles in the triangular pyramid, so the all triangles area is going to be the number of triangles times 1/2 times S times L, or in this case, 1/2 times, we usually use N for the number of sides times the length of each side. Well, the number of sides times the length of each side is simply called the perimeter, right? So the number of sides times the length of each one of these is going to give us the perimeter of that base. And so we're going to frame the context of the area of these lateral faces all together as 1/2 times the perimeter of the base times the slant height. And it's going to feel a little more familiar in the context of the work that we've already done with surface area requiring us to know the perimeter of our base. So therefore, given all that information, the surface area of a pyramid is found by taking 1/2 times the perimeter of the base times the slant height, that's our lateral area, and then add on the area of our base. If our base is a square, then obviously 4 times the length of each side, the length of each side squared. If it's a triangular pyramid, then the triangular base would have a perimeter of 3 times the length of each side. And then the area of that base gets a little bit tricky because we would have to take the length of the side, draw in the altitude, which again would give us a special right triangle, and do 1/2 of the length of this side times that long leg in that 30, 60, 90 triangle. And so half of the side length then times the square root of 3. And so obviously we're going to have to flex that as needed based on our situation. If we have a regular hexagonal base, we might have to do areas 1/2 apothem times perimeter here, and take the number of sides multiplied by how many sides there are. But the surface area of our pyramid is going to be found by taking 1/2 times the perimeter of the base times the slant height, not the height of the pyramid, the height of the triangular faces on the sides, the slant height, plus the area of our base. All right, and so let's go ahead and do this. I have 2 square pyramid examples that we are going to wrestle with here. On this item, letter A, go ahead and do your best drawing of that. Now, with drawing these, it can be a little bit tricky. I tend to draw the triangles kind of at an angle like so, and just I try my best to do that in a way that is visually sound. But it also allows me to draw in that L value, which in this case is 5. 5 yards is equal to the slant height. The side length, the whole side length here is 6 yards, all right? And so when we are doing our formula, we're going to go ahead and write that the surface area is found by taking 1/2 times the perimeter times the slant height plus the area of the one base. When we had prisms and cylinders, we had 2 bases. We've got pyramids and cones, we only have 1 base. And so in this case, we'll have 1/2 times the perimeter, which is 4 sides times 6 yards each. The slant height they gave us here is 5. It was very nice of them to give us that. And then the area of our base is a square. It's 6 by 6. So we'll just take, so you can do 6 times 6 or just 6 squared, however way you want to do that, whichever way. Now, you may have noticed in the first video, I kind of prefer to find the lateral area and the area of the base separately and then add them together. And so I don't know if that is something that you would enjoy either, but here we have half of 24 makes 12 times 5 makes 60. 6 squared is 36, and that gives me the total area of 96 square yards. All right, so we have found the surface area of this pyramid. On this pyramid, things are a little bit different And so pause if you need to get all that information down. But over here, we're going to notice that we're given this 8 meters as the h value. It's kind of hard to see maybe in the video, but there's this kind of dashed boundary, this dashed line that's drawn from the vertex to the center of this base, of this square base. And so that means that we're going to be given this perpendicular distance is 8 meters, and then we have to figure out what is this side so that we can know what the slant height will be there on the back. The way that it's drawn, it's kind of like drawn on the back there. We could draw it this direction if you'd like to see that, but we still need to know the length of this purple segment. Well, the fun thing is, as I mentioned earlier, this purple segment is half of a side. So if a side is 12 meters, then half of a side is going to be 6 meters. All right, so this distance right here is 6, and then let's do our best to find out what L is. All right, and so in this case, we've got a right triangle. It's a little hard to visualize when we're trying to do a three-dimensional rendering in two-dimensional space, but we have the height is 8, we have half of the side length is 6, and we just need to figure out what L is. The good news is that this gives us a Pythagorean triple. 6 squared plus 8 squared equals 10 squared. If that is a struggle for you, you can do all of those steps with a squared and b squared make c squared, which is fine and dandy to add those up, square those up to find out what L is going to be. We have 36 and 64 make L squared. Take our square root to find out that L is equal to 10 meters in this case. All right, so we know the slant height. We can now use our magical formula. Area is 1/2 times the perimeter of the base times the slant height plus the area of the, in this case, a square bottom. And so if there's a triangular base, things would be a little bit different here. For the perimeter, we would take 3 times the length of each side. The area of the base would be maybe a little more difficult to find. But dealing with square pyramids, hopefully this is pretty straightforward. We've got 4 sides times the length of each side is 12, times the slant height we found was 10. Now be aware, the whole side length is 12. We use half of the side over here to find out that slant height. But then we have the area of the base, which is 12 squared. 12 times 12 is 144. So we can just type that in our calculator as is. It would spit out the answer. Again, my recommendation is let's find that lateral area, let's find that area of the base, and then let's add them up. But it obviously doesn't matter. Half of 4 is 2. 2 times 12 is 24. 24 times 10 is 240. That's 144. Adding those together, not too challenging to get 384 square meters. All right, so we were able to find the surface area of 2 square pyramids. Here we were given all the information. We just had to think about how to organize it in our formula. Here we were not given all of the information. We had to do a little bit of work, either mental math, if we know our Pythagorean triples, or a little bit of Pythagorean theorem, which we already know, in order to complete that. So this was working with pyramids, but there's a part due here. There's part 2, and that is dealing with cones. Now cones are, again, they are in the same idea as pyramids, but they have a circular base, all right? The vertex is still the pointy part in the cone, so we're familiar with that idea of theirs being the vertex. The base is a circle. The lateral area is a little bit strange. It's actually a sector of, a percentage of a larger circle. And this distance around is a percentage of a circle that has this radius. This is a little bit hard to envision at this point, but that distance around here is the same as the circumference of this circular base. All right, so that's how our cone works. The altitude of the base, again, is how tall it is from the vertex to the center of the circular base. So that concept of center of a square was maybe a little hard to understand, but center of a circle, I think that we get. The height is that distance. The altitude is the segment. The height is that distance from top to middle. And then the slant height is basically the radius of whatever circle this would be, all right? It is, again, the length of the hypotenuse of a triangle that would be formed using the radius of the base, the height of the cone, and then the outer edge. So this is the radius of the base, this is the height of the cone, and then this would be your slant height. That would be your L value. So it's still going to be an a squared plus b squared equals L squared situation, all right? And we'll be able to use that Just like we did with pyramids, we'll be able to use that here when we work with our cones. Whoops, I have pyramid here. That should say cone. So this is my bad. I'm not going to fix that though. I'll fix it next time we're together. All right. So the surface area of a cone is the same idea. Look at this formula and how it relates to the work that we just did with pyramids. Instead of taking half of the perimeter of the base times the slant height plus the area of the base, it's half of the circles don't have perimeter, they have circumference. Half of the circumference of the base times the slant height plus the area of that circular base. Now you'll notice that I'm using these formulas in general terms. I know that circumference is 2 pi r. I know that half of 2 pi r times L is going to be pi rl, but I'm not going to write pi rl over here. I'm just going to write 1/2 times circumference times the slant height. I think that will make more sense in the sense that you don't have to remember special formula for cone. If you know the formula for pyramid, you also know it for cone. And then you can kind of synthesize those ideas. And of course we have our pi r squared over here. So let's go ahead and actually do a couple of these. You'll notice that we have a similar situation where we are given the radius and we are given the slant height. That's awesome. Here we are given the diameter. We got to understand the radius when we're finding the area. And then we're also given the slant height. I don't have to do a squared plus b squared is c squared here today, but be aware that you might need to do that in your classwork next time. And so again, for this situation, I need to make sure I've got a calculator handy in case I need it for some of this math. The surface area of this cone is 1/2 times the circumference times the slant height plus the area of the base. And so the circumference is 2 times pi times the radius is 8. And the slant height is not 15, this is h, this is L. That's R. So we're going to use L as 17. And then the area of our base is pi times the radius squared. Pi times the radius squared. All right? We could just type this in our calculator without the pi's and it would spit out the answer. But again, we're practicing how to do this work, symbolic math, in terms of pi. The 1/2 and the 2 will cancel. We just have 8 times 17, which is 80 and 56, which adds up to 136 pi. Well, because there's a pi. And then pi times 8 squared is pi times 64, or 64 pi. When I add those together, I get 200 pi square feet. Looks like I didn't need that calculator after all. All right, sometimes I marvel at how my brain's so big. No, I'm just kidding. It's just mental math, folks. But we can, again, use our calculators. 1/2 times 2 times 8 times 17, and that will do the trick. Over here, we have the diameter is 8, so that means that the radius is 4. Sometimes it's helpful to just write down what the radius is. If it's an even number diameter, then writing the radius as the whole number, half of the diameter, is the way to go. Don't write that in your formula as 8/2. It just kind of complicate your work. If it's an odd number, obviously you've got to deal with that. And then here they gave us the slant height of 5. So the surface area is 1/2 times circumference times the slant height plus the area of the base. Let's go ahead and see that we can do this. In fact, go ahead and you do this. You finish this one. You find the circumference of the base, multiply it by 1/2, multiply it by the slant height, and then add on the area of the base, and then we'll confirm whether or not you did that correctly in class. All right, so this is finding the surface area for perimeters. I'm sorry, for perimeters, for pyramids and for cones. You'll notice that the formula of 1/2 CL plus B is the same or very similar to 1/2 plus PL plus B, and that is intentional. You're going to start to see that there's a lot of similarity between finding the surface areas and volumes for these figures. So don't think of this as 4 formulas, think of it as 2 formulas. All right? And don't think that there has to be a unique formula for it. What if it's a rectangular prism? What if it's a triangular prism? What if it's a hexagonal prism? What if it's a pyramid versus a cone versus a hexagonal pyramid, a square pyramid, whatever, triangular pyramid? Don't think of them as separate formulas. Think of them as one concept. Half of the distance around the base times the slant height plus the area of the base. All right? And then you can kind of just think between perimeter of prism's base, circumference of cylinder's base, perimeter of pyramid's base, circumference of cone's base. So the notation that we use should aid you in writing those formulas well so that you know those formulas well so that you can be successful in this unit. That is it for now, finding the areas for perimeters and cones. That was lesson 2.